Hello, this is the first video on energy. So your book points out in this first section that energy is a pretty sacred thing in physics. A lot of the stuff that we've done before on forces isn't really used in like studies in graduate school. We don't really talk about forces very much, but we do use energy all the time. Energy is a definition that we're going to go over in this video. And it's a tool that you will use throughout physics. So this is really essential stuff here. We'll be able to answer this problem. I'll come back to this, but there's a lot we need to introduce first. So just to give you an idea of where we're going, the goal of this video, other than to be able to solve that problem, is to explain this formula. And this formula is called the work-energy theorem. This formula is the sum of all the works done on an object is equal to the change in that object's kinetic energy. Okay, so you might see it as delta KE, you might just see it as delta K. Okay, so this is a very concise way of writing it. And this introduces two terms that we haven't talked about yet in this course. So on the right-hand side, it's kinetic energy. And on the left-hand side, it's work. So we need to talk about each of these two things. So this is change in kinetic energy. And this is the sum of all the works done on an object, or the net work on an object. All right. So, I think I'll talk about this one first and then this one afterward. Your book is kind of talking about both at the same time. It's almost deriving this work energy theorem. You can get a feel for this right here. So it's something minus something equals F times D. So it's the change in kinetic energy is on the left-hand side there, and then the work is on the right-hand side. But it's making a lot of assumptions, and so I think it can be a little misleading to just start off with this. So I'll talk about what your textbook does after we talk about each of these two things separately. Okay, so the first thing. So we're going to define something called an energy of motion. We define an energy of motion called the kinetic energy. So kinetic energy, you might see it written as Ke, you might see it as just K. It's 1/2 mv squared. Okay, so the 1/2 is kind of mysterious, and it doesn't really make sense why that might appear. It appears so that this equation could be true, so that work energy theorem could be true. But then that's also going to depend on the definition for W. So what I want to talk about is this definition is sort of intuitive, maybe not the squared part of it, but the faster something is moving, the more energy it has. I think that part's okay. It's not so obvious why it's v squared rather than v. So you might wonder, well, why didn't we define something called m times v? So it turns out we do use that for another reason. That's going to be related to momentum. So we're going to define something else later on in a later chapter called momentum, and that will be m times v. Okay, so mv is useful, but not for us yet. So this quantity is even more dependent on speed. So if you double speed, you actually increase your energy of motion by a factor of 4. You increase your kinetic energy by a factor of 4. And then it makes sense, if you have a car moving at 50 miles an hour, there's more energy there than a fly moving at 50 miles an hour. So the fact that it's proportional to mass is probably not too surprising. And then a car, you could split it in half and it's moving, and there's really not much of a difference in terms of a car moving at 50 miles an hour or like 2/2 of a car moving at 50 miles an hour. So the fact that it's proportional to m is not too surprising either. What's interesting about this also is that this is a scalar quantity. There's no direction here. This is a scalar. Sorry for the handwriting. Scalar, not a vector. So this quantity is just a number. Energy is a number. This other thing that I talked about, momentum, that will actually be a vector quantity. But energy is just a number. And the units here are, so in SI units, the units of energy are kilograms. So it's the SI unit for mass, the SI unit for speed or velocity squared. So it's kilograms meters squared per second squared. And we give this a name. This is a joule, capital J. The definition for a joule is just a kilogram times a meter squared divided by a second squared. So there's nothing, it's not really a new unit. It's not a new dimension in the sense that we can say that energy is mass times length squared over time squared. So the dimensions of energy we can rewrite in terms of base dimensions, or in other words, in terms of units. The joule we can rewrite in terms of our 3 base SI units, kilograms, meters, and seconds. Remember, mass, length, and time, we can build up all of these things in terms of that. Okay, so dimensions, energy, SI units, joules. Non-SI units, actually joules is probably the most common. Maybe you've heard of calories. That's another unit for energy. It's not, we don't generally use calories for kinetic energy, but for heat. And so you'll learn a lot more about that in 4B. There's a conversion between joules and calories. There's a difference between food calories and calories, but that's for another day. Okay, so we just need to recognize that anytime we see 1/2 mv squared, you know that the object just has one speed. The object just has one kinetic energy. Okay, so it's just the recognition of anytime we see this 1/2 mv squared, that's the kinetic energy of the object. Okay, now this other thing, so what is work? So this equation must be saying something. What is it saying? It's talking about change in energy of motion. So the way to change the kinetic energy of an object, we have to do work on it. So this is going to be a slightly different definition than what you might be used to. So we'll talk about some of the differences in a bit. So to give you a general sense of what work is, so very informally, work is, so for one thing, it's force over a distance, force times distance. The way you probably want to think about work is the force giving energy to the object, or is it taking away energy from the object? So it's keeping track of, so our definition for work is going to be such that it keeps track of whether, W-H-E-T-H-E-R, of whether a force is giving energy to an object. So in that case, the work will be positive, or taking it away, or taking energy away, in which case the work is negative. So the work, just like kinetic energy, we're using K or KE, the work we're using W. Now our definition of force times distance, so the full general statement is that the work is the integral of the force on the object times the differential displacement that object is making. So the object is moving from some initial position to some final position. And as the particle moves along, it's moving in maybe all sorts of certain different directions. You know, if this is the initial spot and this is the final spot, you break up its motion into a bunch of little pieces. And the small amount of displacement that it makes, that's what this dr is. So it involves a dot product between some force, so this might be our dr, and then the force on the object, there could be several forces on the object. So maybe one force is perpendicular at that moment. So if F is perpendicular to dr, then the work is 0. So because of that dot product, the work is 0. So in this case, The work is 0. So what that's saying is that if a force is perpendicular to the direction of motion of an object, it's neither giving energy to the object nor taking energy away. Okay, and you can see from this dot product the other two cases of positive and negative. So if the force has a component that's along the direction of motion, then it's kind of boosting the object, it's speeding it up, and it's giving energy of motion to it. It's giving work. There's a positive work. And vice versa. So if the force is opposite the direction of motion, or if there's a component of the force opposite the direction of motion, then the work is negative and the object is being slowed down by that force. Right? Maybe it doesn't slow down overall because there's other forces on it, but the action of that force is to slow it down. So one other thing I want to mention, let me make room for it here. So I'm going to bring this down here. One other thing about work is that it's a transfer of energy. So energy is some quantity. Energy is different from force because a force is not something you can give to someone else. You can't give 3 newtons of force. I'm going to give it to my friend, 3 newtons of force. No. Remember, force is an interaction. Energy is different in that it is a quantity that you can give and take to an object. Okay, an object has a certain amount of kinetic energy. You can give that object energy by doing positive work on it, or you could take away some energy from that object by doing negative work on it. Okay, so work is keeping track of transfers of energy from one object to another. Okay. So this is the fully general formula, and then there's a couple common ways to simplify it. So there's 2 different kinds of simplifications. We could say that F is constant, or we could specialize to the case of one dimension. And your book actually does both of these things. So I'll combine these 2 simplifications in just a second. If F is constant, we can take it out of the integral sign here, and then integral dr is delta r. So if F is constant, we can write work is F dot delta r, the whole displacement. Because as r moves from its initial to its final position, F is constant. So we can take it out of the integrand, so it makes sense. The 1D case means that dot product is just multiplying 2 numbers. F is either positive or negative. F maybe depends on x, dx. So I'm using the letter r to indicate that it could be more than one dimension. X is kind of the default for one-dimensional motion. So this object is moving from some initial x spot to some final x spot, and then F is either positive or negative. So you're just summing up a bunch of positive or negative numbers to get your overall work. So then if both of these things are true, so if F is constant, so both, then you can say that the work done by the force is F times delta x. And your book just calls that F times d. So there's a lot of assumptions to get to that right there, F times d. Or F times d, according to your book, your textbook. So your textbook first is just talking about one dimension, and it's also talking about the case where F is constant to get there. And there's actually one more simplification in there, which I guess I'll mention right now. So remember there can be more than one force on an object. Multiple forces on an object. So there can be multiple works on an object. So for every force, you look at what that force does as the object moves over a certain distance. If the object doesn't move, then there's no work. That's another thing that this equation is implying. If dr is always 0, you're adding up a bunch of zeros, so there's no work. There can be multiple forces on an object, so there can be multiple works. You can keep track of what's the work done on an object by F1 versus the work done by F2 versus the work done by F3, etc. So we'll sometimes talk about the net work, or the sum of all the works. So this is the net work done on an object. This is the sum of all the works. And our work energy theorem, to get back to our starting point, is that if we add up all the things that are either giving energy to the object or taking energy away, then the overall effect is the change in kinetic energy of that object. Delta K or delta KE. This is the work energy theorem. Now your book proves this for these special cases, under these simplifying assumptions. So your book is doing a lot because your book takes this equation for kinematics. V final squared is V initial squared plus 2a delta x. And they replace A with F over m. See Newton's second law right there? So what assumption are they making? Maybe you can pause and try and figure it out. The assumption that they're making is that the net force is just from a single force F. So when I say right here that there can be multiple forces on an object, they're just assuming one force, and so the net force is the same thing as that one force. But in general, to replace A with F, you would take this A and you would replace it with F net, right? So when I say the net force, the net work versus a work from a single force, your book is glossing over that and just saying that they're the same thing. So your book rewrites this, and then you could probably figure out that you could put the mass, you can multiply the whole equation by mass and divide by 2, and then rearrange it to get this. This is change in kinetic energy, 1/2 mv final squared minus 1/2 mv initial squared equals, and then that's the work done by a constant force in one dimension. So if F is positive and the displacement's positive, then there's positive work done. If F is negative and the displacement's negative, then that's also positive work. You're also speeding up the object. So that means the object's moving in the negative direction, and you're also boosting it along in the negative direction. Okay. So maybe one last thing, and then we're in a position to do that example problem, and that is the definition of power. Oh, so well, even before power, I just want to mention that if you double check Newton times a meter, and you rewrite Newton in terms of these other things, you can show that a Newton times a meter is also a joule. So maybe we can just add to this right here. So a Newton times a meter, so kilogram, so I'm just rewriting what we had before, kilogram meter squared per second squared. So a kilogram times a meter divided by second squared is a Newton. So we still have a factor of meters left, meters left over. Newton times meters is also equal to joules. So the units work out here. So the units of work are also joules. The dimensions of work are energy. Okay, so work and energy have the same dimensions, which is why we can just say that they're equal like this. There's no constant in front relating these two. Okay, power is something with different dimensions. So power is talking about how quickly you're doing work on an object. So for every force doing work on an object, positive, negative, or zero, there's some power associated with it. Power of a force. So the power done on an object by a force is equal to the rate at which it's doing work on an object. So dWd time. So like if my car is not great, it takes a long time for my car to get onto the freeway, to get up to 65 miles an hour. Now the change in kinetic energy is 1/2 mv final squared, where v final is 65 miles an hour. A Porsche, a fancy car, could do that same amount of work, that same positive work, the engine doing positive work to get so that the change in kinetic energy of the car could be positive. It's the same amount of work, but in a lot less time. And the reason it can do that, the reason a fast car can do that, is because it has a lot of power. So the same change in work, but in a much smaller time, is a bigger power. This is the rate at which work is being done by that force. And it's also equal to F dot V. So this is actually fully general, F dot V. Your book, again, is simplifying, saying one-dimensional case. So there's no dot product. But even in multiple dimensions, even if F is not constant, this is the instantaneous value of the power. So this is the power done by a force at a particular instant in time. So maybe that power is changing, but this is for any instant. So the units here are different, right? It's joules per second. So the dimensions are power. And the SI units are something we call watts. So this is a joule divided by a second, right? Just looking at this equation, it has to be the units for energy divided by the units for time. It's joules divided by seconds, and that's called watts, capital W. So the SI unit for power is watts. Another common unit is horsepower. So 1 horsepower for like your car's engine is about 750 watts. I think that's about right. But in this class, we're going to use watts a lot more than horsepower or BTU or anything like that. Okay. Yeah, watts and joules. Okay, back to the original problem. So let's go all the way up. We have a person pushing some box with an applied force F applied, and we're told the box is moving at some speed V naught. And there's friction, which is why they need to push. Okay, so there are 4 forces on the box, as alluded to in part A. What is the work done by each of those 4 forces? Okay, so let's draw the free body diagram for this. So we have a box, we have F applied to the right, that we're given. The frictional force, we're not told anything about it, but we know it has to equal in magnitude to the applied force. Just because we're told it's moving at constant velocity v naught. There's normal force, and then there's mg. So we're not given the mass, but just labeling the free body diagram. Looks like that. So A, what is the work done by each force? Work done by each force. What is the work done by each? Well, so for example, the applied force, F applied is to the right, and it looks like the person is pushing, so the box is moving to the right. So the person's applied force is doing positive work on the box. So for F applied, this is positive work. But the amount of work depends on how far the box slides. Okay, so the work done by the applied force on the box is equal to F applied times the distance that it travels. So let's say the box slides a distance d. So by the way, if you've seen stuff about work before and you saw the problem and you were confused, you know, how could you answer this problem? There's not enough info given. You're right. There was not enough info given. Right? So the work done by the applied force, it depends on how far that box was sliding. So however far it slides, some distance d, that's how much work is done. So if you double the amount of time, it's double the amount of work done by that applied force. The frictional force is doing negative work. So the work done by that frictional force is equal to negative F applied times whatever distance that the block travels. Okay, the frictional force is to the left, the box's displacement is to the right, and so that dot product is negative. Right, it's the magnitude of one of the vectors, so the magnitude of the frictional force is F applied, times the magnitude of the displacement times the cosine of 180 degrees, which is -1. Okay, so friction is taking energy away from the box. So you're giving the box energy, but at the same time, the kinetic frictional force is taking that energy away. And for every amount that you give it, the frictional force is taking that away. And then now the gravitational force and the normal force do no work. since these forces are perpendicular. To the displacement of the object. So the gravitational force is down and the box is moving to the right, that's 90 degrees. Normal force is up and the box is moving to the right, that's 90 degrees. So dot product between those, between either of these two forces and the displacement is 0. That dot product is 0. Okay, no work is done. And that makes sense. If the normal force is not tending to speed the thing up, it's not trying to slow it down. So it's not doing positive or negative work on the box. Show that the work energy theorem is satisfied. Well, looks like, so there are two works, and then the other two are equal and opposite. So for part B, the sum of all the works is 0. It's F applied times the displacement minus F applied times the displacement is equal to 0. Okay, the change in kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared. And we're told that the speed is constant. Okay, so if the speed is constant, the final speed is equal to the initial speed. And that's equal to 0. So the sum of the works is equal to the change in kinetic energy. I don't know how much that constitutes a proof because we sort of had to use the fact that it was moving at constant speed in order to show that the frictional force had the same magnitude, or sorry, the work done by friction had the same magnitude as the work done by the applied force. But at least it's consistent with the work energy theorem. So we don't have any inconsistencies or anything. Then part C, the power done by each force. Well, remember that's the force dot with the instantaneous velocity of the object. So the applied force is to the right, and so the power by that applied force. The applied force is to the right, the box is moving to the right with some speed v naught. So this is F applied times v naught, and positive. The power from the frictional force is equal and opposite to that. And then the power from the other two forces is 0, because there's no work done by either of those two forces. So remember I said that the work done depends on how much time that box has slid, but the power from each of these forces is constant. So for a constant applied force and a constant speed, the power is constant. So the rate at which you're putting energy into the system, the rate at which you're giving energy to the box is constant, but then the frictional force is taking it away at that same rate. And so overall, the box isn't speeding up or slowing down because there's no net work done on the box. There's no overall work done on the box. Okay, so your book just talks about calculus a little bit. So in a case that the force is not constant, it talks about taking the integral of f dx for each of those forces. And then see this equation right here, the fact that they set f dx equal to dk instead of dw, since it's not work but kinetic energy, that tells me they've already used the work energy theorem. So they're assuming here in this equation that F is the only force acting on the object. Right. So work energy theorem again, and then your book talks about the fundamental theorem of calculus in that last page. Okay.